Embedded engineering is where abstract logic crashes into physical reality. At the microscopic level, software is nothing more than electrical pulses navigating complex silicon pathways. Modern consumer computing hides these physical details. When you write code for a laptop, an operating system sits between your logic and the hardware, managing memory and physical voltage. But in embedded systems, there is no safety net. You control the hardware directly. This is the Intel 8051, an 8-bit microcontroller. Released in 1981, it is the enduring foundational tool for learning how to control bare metal. The 8051 is a system on a chip, or SoC. An SoC is an integrated circuit that combines all the essential components of a computer, like the central processing unit, memory, and input-output ports, onto a single piece of silicon. We still study the 8051 today because it is completely transparent. It forces students to confront the unforgiving realities of hardware-software co-design, where a single line of code must align perfectly with the physical constraints of the chip. The 8051 comes in a standard 40-pin dual inline package. This physical form factor dictates everything. Every software instruction you write is ultimately bound by these 40 physical copper connections to the outside world. This animated schematic details the 40-pin layout. To make this architecture digestible, we can divide these pins into distinct functional groups: power and timing, control, and input-output lines. Look at the red power pins. Pin 40 is VCC, which requires a steady plus 5 volts of direct current. Pin 20 is the ground connection. Without these two pins properly wired, the chip is completely dead. Next to them are pins 18 and 19, labeled XTAL1 and XTAL2. These connect to an external 12 MHz crystal oscillator and a pair of capacitors. An oscillator is an electronic circuit that produces a repetitive, oscillating electronic signal, acting as the system's mechanical heartbeat. This external crystal generates the strict machine cycles that time every single internal operation the CPU performs. Every line of assembly code takes a highly specific number of these clock cycles to execute. Moving to the yellow control pins, pin 9 is the reset input. Applying an active high electrical pulse to this pin immediately terminates all chip activities and resets the system back to its default state. Then there is pin 31, the external access pin. This connection dictates whether the chip reads its program instructions from its own internal memory or looks outward to external read-only memory modules. The entire microcontroller is slaved to these physical boundaries. If you fail to supply external power or that precise clock heartbeat, you are left with an inert piece of silicon. Of the 40 available pins, 32 are designated for input and output. These are divided equally into 4 8-bit ports, labeled port 0 through port 3. This introduces a concept called pin multiplexing. Multiplexing is an engineering technique where multiple internal signals or functions share the same physical output line. It is a necessary compromise to fit complex capabilities onto a physically small package. This focused view of port 3 is the perfect example of this dual functionality. In its standard configuration, port 3 acts exactly like the other ports, providing general-purpose 8-bit input and output. But these exact same physical pins also serve alternate functions routed directly to internal peripherals. They handle serial data communication, specifically receiving and transmitting data, as well as triggering hardware interrupts. Pin multiplexing forces the embedded engineer to make deliberate design trade-offs. You have to decide exactly how these limited physical connections will be utilized by the software, because a pin cannot perform both roles simultaneously. Once we look past the external copper pins, we map the logic pathways etched into the silicon die itself. The structural philosophy of the 8051 is built entirely around the Harvard architecture. This block diagram shows the internal architecture of the 8051. You can clearly see the strict physical segregation between the program memory blocks, labeled flash or ROM, and the data memory, labeled RAM. Notice the distinct internal bus lines. The chip uses separate pathways to fetch instructions from its 4 kilobytes of on-chip ROM and entirely different pathways to read or write data to the internal RAM. This structure differs from standard desktop computers, which generally use the von Neumann architecture. A von Neumann processor shares a single data bus for both code and data, creating a potential bottleneck if the system tries to fetch an instruction and read memory at the exact same time. At the center of the diagram is the 8-bit CPU. This includes the arithmetic logic unit, the accumulator, and the B register. The accumulator is the primary register where all arithmetic and logical operations are calculated. The Harvard architecture physically enforces this division of instruction and execution. It optimizes the chip for highly reliable, single-purpose embedded tasks without the risk of data collisions on a shared bus. When we look at that internal RAM, we find a severely limited workspace. The standard 8051 provides exactly 128 bytes of internal random access memory. This memory map illustrates how those 128 bytes are heavily structured. They are mapped from address 00 hexadecimal to 7F hexadecimal and divided into 3 specific functional groups. The lowest 32 bytes, from address 00 to 1F, are strictly dedicated to 4 separate register banks, each containing 8 working registers labeled R0 through R7. Only one of these 4 banks can be active at a time. The programmer selects the active bank dynamically by toggling 2 specific bits inside the program status word, or PSW, register located higher up in the architecture. Just above the register banks, from address 20 to 2F, we find 16 bytes of bit addressable memory. Bit addressability is an incredibly powerful feature for an embedded system. It allows a programmer to alter a single Boolean variable, a simple 1 or a 0, without wasting clock cycles reading, masking, and rewriting an entire 8-bit byte. Finally, the remaining 80 bytes, from address 30 to 7F, serve as a general scratchpad for reading, writing, and storing temporary data. This hyper-structured RAM map forces students to manage memory resources with microscopic precision. You cannot afford to waste a single byte when your total available workspace is smaller than a short text message. The ultimate goal of embedded engineering is translating all this abstract internal logic into a tangible hardware action. It is the exact moment when a high or low value inside a data register travels outward as a sudden physical voltage spike. This diagram illustrates turning on an LED connected to port 1, pin 0. An assembly instruction drops a logical 1 into the latch for port 1.0. This drives the internal bus, pushing the external pin to 5 volts, completing the circuit to illuminate the LED. The 8051 remains the pedagogical gold standard because it shrinks the vast complexity of computing down to a visible, tactile reality. It proves to engineers that, at the lowest level, code and copper are exactly the same thing.
Thanks for watching. Please visit the channel for more content and don't forget to subscribe and like if it was helpful. Comment if something is wrong.